Yes, students. Today, we are starting our first module, and the first module deals with the advanced internet working concepts. So, before starting, let me draw your attention to some of the terms used in internet working. Okay. After that, we can discuss the concepts of advanced internet working. So, don't worry, I have attached the PPT of internet working also in my drive. You can go through it, and let me take your attention to familiar some of the keywords. What do we mean by internet work? Internet work we can define it is an arbitrary collection of networks interconnected to provide some sort of host to host packet delivery services. You have learned about packets, datagrams, and all. So you have to just go through the packet format, the submitting concepts, classless addressing modes, and all. Then I think you're familiar with the switching, the forwarding of packets, different topologies in the network. That means star topology and all. You have to get familiarization about the bridges and LAN switches, which uses the spanning tree algorithms for um, ARP protocol, that means address translation protocol. It's conversion, IP conversion, ARP, RARP. Then you have to familiar the host configuration, dynamic host configuration protocol, internet control message protocol. Then different routing algorithms, that is distance vector algorithm. You have to refer the count to infinity problem. Then the other algorithm, information protocol, routing information protocol, that is RIP. Then link state routing. Then open short path, shortest path first routing, OSPF. These are all algorithms you have studied in your previous semester. That means on your BTech sessions. So these are all various concepts in internetworking, and now we are moving to the advanced internetworking concept. And in this session, we will just discuss about the problems which we are facing in internetworking. First, we have to build a large, or we have to scale our smallest internet to internet working, or scaling to billion. How we could build a routing system that can handle hundreds of thousands of millions of networks to billions of end nodes. Then how we will handle the address space exhausted by IPv4. I think all are familiar with the IPv4 format, IPv6 format, which we have studied in beta classes. Just here in this module, the syllabus goes for the discussion of IPv6. We will discuss that, and before that, we will just go for the IPv4 also. So in this module, we have to handle the issues of routing system, how we will able to scale the inter networking nodes to billion nodes. Then we have to discuss the problems of addressing space exhaustion. Then what are the enhanced facilities or functionalities of internet like multicasting, mobile IP, like that. So the chapter outline global internet, multicast, and mobile IP. It's just small insights of what our chapter discuss. Okay, okay. The next slide. First, the heading on the syllabus is the global internet. What comes to your mind when we think about the global internet? First, we are browsing, and when we have any buffering, we will feel exhausted. I need more speedy internet. So let us think about a small bit of history about this internet, which we have studied in smaller classes, 8th standard, 9th standard on. All are familiar with the history of internet, which starts with ARPANET, then it was NestNet. I think it's for only for military communication where we have used internet in the early days. That means before in 90s and all. Okay. Then after that, many internet service providers came, many different packages, different offers. Everyone, everyone is using internet and every information at its fingertip. So when we think about internet, we have to deal internet working. We have to deal with two sorts of problem, that is heterogeneity and the scalability. These both things are contradicts because heterogeneity means the internet or we are connecting different kinds of devices. That means in the networking concept, we can say it as nodes. Okay, nodes, NODES. Different devices and different devices is working with different protocol where everyone is connecting to this global internet. So heterogeneity, we have to sort that issue. Then scalability, we have to increase the number of devices. At the same time, we should get the internet speed also. We have everyone should access the internet with the same speed, but we should add more devices. So a hierarchy structure will be able to tackle the scaling issue. Heterogeneity, we have to able to add more devices. At the same time, we have most approaches to tackle the scalability of routing depends on the introduction of hierarchy. Uh, Earlier in the starting of the session, I have mentioned about different routing algorithms and all. They're all we use a hierarchy. Okay. Then what all scalability issue we can there and there comes the addressing mechanism. IPv4 is 32-bit addressing scheme, so we are fetching for IPv6. So IPv5 is there, but it is an experimental basis. It does not come into existence. We have only IP address IPv4 version. That means IP version 4, IP version 6. So in this module, we will discuss about it and all. Then global internet, what comes to it's a what we can say it's a heterogeneous collection of networks to create internet network. We have a simple hierarchy of IP address to make the routing in an internet, which will be scalable. Then a routing protocol, which we will discuss later. Then one of the important term I have to tell here is autonomous system. Okay. Nowadays, each internet service provider throughout this module, we are giving a term autonomous system. Okay. Don't forget the term autonomous system. Here I have shown a figure. It's a tree-like structure of internet in 1990. Uh, why we are adopting this tree structure? One of the salient feature of this topology is that it consists of end user side. For example, here you can say Stanford University that connect to the service provider network, Baranet, which is a provider network in San Francisco area. So in 1990s, many providers served a limited geographic region, but is known as regional network. In that region, we are providing. Then these regional networks in turn connected to the nationwide backbone. In 1990s, the backbone was funded by National Science Foundation, NSF. So in NFSnet is the backbone. Then you can look into the figure. The provider network are then built into a larger point-to-point links. Then that connects. So each end user site is typically is not a single network, but instead consists of multiple physical network connected to the routers as well as for the bridges. So don't forget the term autonomous system that we can tell in a short form as A. This only comes for global internet concept. That means our internet is very, very uh, scalable as well as heterogeneous. Heterogeneous means a number of different kinds of nodes can be or devices can be connected to the network. And the scalability issues can be sorted out by using a hierarchy structure. So next we are okay. Then next we are introducing routing areas. So all are familiar with routers. So routing area, already we have known about different link state routing protocols, and they use a partition. That means they are dividing it into various areas or domains or subdomains. So routing domain into subdomains known as areas. We using area. It's a terminology in OSPF, open source, open state, shortest path first routing. We use the terminology throughout this module. So, what is this area of area means? Is it's a set of routers that are administratively configured to exchange the link state information with each other. Then one special area, the backbone area, we will name it as area 0. You can look into the figure, area 0. An example of routing domain divided into areas. Then R1, R2, and R3 are the members of backbone area. Here the backbone area is shaded with a blue color. There are also members of at least one non-backbone area. Then R1 is actually the member of area 1 as well as area 2. The router that is a member of both backbone area and a non-backbone area is an area border router. Area border router ABR. Note that these are the distinct from the routers that are at the edge of an AS. AS means here it is an autonomous system, which is referred to as AS border routers for clarity. So that means we are in our discussion, we are mentioning area border router as well as AS border router, border router. Then all the routers in the area send the link state in advertisements, informations or advertisement to each other and thus develop a complete consistent map of the area. The link state advertisement of routers that are not area border router do not leave the area in which they are originated. They has the effect of making the flooding and route calculation process considerably more scalable. For example, R4, the router 4 in the area 3 will never see the link state advertisement from router 8 in area 1. As a consequence, it will know nothing about the detailed topology of the areas other than its own. So, how the router in one area determine the right next hop of the packet destined to a network in other area? Um, Okay, imagine the path of a packet that has to travel from one non-backbone area to another as being split into three parts. First, it have to travel from its source network to the backbone area. Then it have to cross the backbone. Then have to travel from the backbone to the destination network. How this make it work? The area border routers summarize the routing information that they have learned from one area, make it available in their advertisements to other area. For example, here R1 receives the link state advertisements from all routers in area 1 and can thus determine the cost of reaching any network in area 1. Then R1 sends link state in advertisements into area 0. It advertises the cost of reaching the network in area 1 much as if all the networks were directly connected to R1. This enables all the area 0 routers to learn the cost to reach all network in area 1, and the area border router then summarizes this information, advertise it into the non-backbone area, and all routers learn how to reach all networks in the domain. In the case, area 2, there are two. ABRs. That means area border router. Here I have mentioned the short form also. And that routers in area 2 will thus have to make a choice as to which one they have to use to reach the backbone area. This is easy since R1 and R2 will be advertising the cost to various network. So it will become clear which will the better choice for routers in area 2 run the shortest path algorithm. Then R1 is going to be the better choice than R2. It's very pretty clear to reach the destination area 1. When dividing the domain into areas, the network administrator will make a trade-off between the scalability and optimality of routing. The use of area forces all packets travel from one area to other and back to backbone area, even if the router path might have been available. Here, for example, in R4 and R5 are directly connected, and the packets would not flow between them because they are in different non-backbone areas. In turn, that the need for scalability is important and the need to use the absolute shortest path. This illustrates a very important principle in network design. That means here this division into domains. There is frequently a trade off between some sorts of optimality and scalability. When the hierarchy is introduced, the information is hidden from some nodes in the network, hindering their ability to make a perfectly optimal decisions. However, information hiding is essential to scalability since it saves all nodes from having a global knowledge. It is invariably true in larger networks that scalability is more pressing design goal than a perfect optimality. There is a trick which the network administrator makes can be more flexibly designed which router have to go in area 0 and in the trick they uses the virtual link between the routers. But the virtual link is obtained by configuring a router that is not directly connected to area 0 to exchange backbone routing information with a router that is. For example, a virtual link could be configured from R8, that is router 8 to router 1, R1, thus making R8 the part of backbone. R8 would now participate in link state advertisement flooding with other routers in area 0. The cost of virtual link from R8 to R1 is determined by the exchange of information that takes place in area 1, and this technique help to improve the optimality of routing. So that's the end of today's discussion. Thank you.